Hi folks, we're going to take a look at a typical multi-step work problem here. So let's take a look at the question. We've got someone carrying up a container holding sand up a 10-meter ladder at a constant pace, and the container itself has a mass of 15 kilograms, and we're starting off with 20 kilograms of sand. However, the sand is leaking out at a constant rate so that the last grain falls out just as you reach the top of the ladder. Moreover, it's raining, and the rain is accumulating in the container at a rate of 0.5 kilograms per meters climbed. And we want to calculate the total work required to carry up this container. So the way in which we solve these is we look at each component separately. So we're going to determine the work needed to carry up the container alone, the mass alone, and then the rain alone, and then add everything up to get our total work. So let's start with the easiest one, and that would be the container, because the mass stays constant throughout the process, hence the force is constant, and we can calculate the work directly just using our formula: work equals force times displacement. So we have the force is just the mass, which is 15 kilograms, times the force due to gravity, which is, the acceleration due to gravity, which is 9.8. And we calculate that to be 147 newtons. And so the work, which is just force times displacement, would just be 147 times our total displacement of 10 meters. So we have 1,470 joules is the work required to carry up just the container. So now we'll head off and do the sand. Now, of course, this is not quite so easy because the sand's leaking out, meaning the mass is changing as we're moving up the ladder. So what we can do is just draw ourselves a little graph here. And what we want to measure is the mass of the sand with respect to x, which would be the distance traveled. Okay, and we're starting off with 20 kilograms of sand, eventually ending up with none. And that occurs right as we reach the top, so 10. So we've got this line here. So we can come up with an equation for the mass of the sand. It's just a linear equation, just be 20. And the slope of this line is just -2, so 20 minus 2x. Okay. Now what we want to do is determine the work. So as we often do is we'll take our 10-meter ladder, or 10-meter distance that we have to cover, and we'll split it up into a partition, and in particular we'll look at one partition. So if we call this xi minus 1 to xi, and we'll assume that the mass can be considered constant in a small subinterval. Okay, so we'll need to choose our usual representative in that subinterval, which we usually call Ci, and we'll calculate the mass and the force needed to hold up the container at that particular value. So we've got the force at Ci will just be the mass, 20 minus 2 times Ci, times again acceleration due to gravity 9.8, and so we have here 196 minus 19.6 Ci. Okay, and we use this to calculate the work to carry up the sand up that small distance over the subinterval. So that will just be F at Ci times the displacement, which will be delta xi. And so we have 196 minus 19.6 Ci times delta xi. And as we normally do, we now sum up all the work for each of the subintervals. So the work can be approximated by the sum of all these subintervals. So we've got 196 minus 19.6 Ci times delta xi. And if we look at this function here, we notice that that's a continuous function, hence integrable. And so we can calculate the true work required by taking the limit as our partitions go to 0, which will then give us the integral from 0 to 10 of 196 minus 19.6, and of course the CI becomes our x, and delta xi becomes our dx. Okay, that's an easy integral to solve, so you can do that on your own or just put in a graphing calculator, and what we get here is 980 joules. Okay, so now we're going to take a look at the work required to bring up the water. Okay, and we have a similar situation as we did with the sand, in that the mass of the water is changing over time. Okay, so again, draw myself on a little graph. I start off with no water, and eventually it just keeps accumulating at a constant rate. Now we already know the rate of change, and we know that it starts at 0, so we can write very quickly that the mass of the water is just given by 0.5x, where again x is the distance traveled up the ladder. Okay, and yet again we take our ladder and we split it up into subintervals, and we assume that the mass of the water can be considered constant in a small subinterval. So we're going to take a CI in that subinterval to represent the mass within that whole subinterval. So again, we've got the force at CI can just be calculated by 0.5 CI times 9.8. Okay. So here we've got 4.9 CI. Okay, so to calculate the work to carry up the water up that small subinterval is just given by again 4.9 CI. The force times the displacement will just be delta xi. So as usual, we estimate the total work by summing up all the work of each subinterval. Okay, now again, a nice easy integrable function, so we know that we can take the limit and get the true work as the integral from 0 to 10 of 4.9 x dx, and again, easy integral to solve. You can get that as 245 joules. Okay, so now what we're going to do, make a bit of room and calculate the total work required. So the work will be the work for the container plus the work for the sand plus the work for the water, and so we've got 1470 joules plus our 980 joules for the sand plus our 245 joules for the water, giving us a total of 2,695 joules to complete this task. Okay, so just repeat. What we did is we took each part separately. Anything for which the force did not change, or the force was constant throughout, you just multiply the force times the displacement. However, when the force does change as time goes on, this is where you set up your Riemann sum to calculate your work in a small subinterval, and then sum it up and hopefully get a continuous function that allows you to take the integral to calculate the total work. Okay, that's it.